Welcome back, everyone, to the part four of the lecture series, or the informed reading of Introduction to Chaos Theory. And we'll start back where we left off with the arrival of a scientist called Ilya Prigozhin and the specific theory which he brought to the scientific community, which is the theory of dissipative systems. The Belgian chemist Ilya Prigozhin, born 1917, is one of the true pioneers of chaos. In 1977, he won the Nobel Prize in Chemistry for his work on dissipative structures. Prigozhin was the first to introduce the notions of dissipative systems and self-organization, and to show that conditions which give birth to structures are far from equilibrium. Some parts of the universe are closed areas that operate like machines, but they form only a small part of the universe. Most other areas are open and exchange energy or information with their environment. Biological and social systems are open. Therefore, understanding them in mechanical terms will not work. Most of reality is not stable, but full of disorder and change. Disorder to order. Prigozhin differentiates between systems in equilibrium, near equilibrium, and far from equilibrium. A small population where the addition of a few births and deaths does not greatly affect the situation is in equilibrium. However, if the birth rate were suddenly to rise uncontrollably, then strange things could happen. It is far from equilibrium. In far from equilibrium systems, we can see matter being dramatically reorganized. There is a transformation from disorder, thermal chaos, into order. New dynamic states of matter may originate, states that reflect the interaction of a given system with its surroundings. Prigozhin called these structures dissipative structures because they require more energy to sustain them. In general, dissipative structures involve some damping process, like friction. Self-organization and time. Moreover, when a far from equilibrium system enters a chaotic period, it changes into a different level of order, spontaneously, through what Prigozhin called self-organization. Initially, Prigozhin's ideas on self-organization were highly controversial. He also brought time into the equation of chaos and complexity. Time is what keeps everything from happening at once. Time and the problem of entropy. In Newtonian physics, time was an afterthought. Newton thought that each moment was like any other. The machine can run forwards and backwards. It doesn't really matter. However, thermodynamics and its crucial second law placed time in a central position. The machine is running down, and time can only run one way. You cannot make up for entropy. The universe faces heat, death. Prigozhin argued that time could only appear with randomness. Only when a system behaves in a sufficiently random way may the difference between past and future, and therefore irreversibility, enter its description. The source of order. In some chemical reactions, two liquids mixed together diffuse until the liquid is homogeneous. They do not de-diffuse themselves. At each moment, the liquid is different and therefore time-oriented. Chemists regarded this as an anomaly. These one-way, time-dependent processes are not anomalies. The opposite may be true. Closed systems with reversible time could be the abnormality. Irreversible processes are in fact the source of order. Hence the title of Prigozhin's most famous book, order out of chaos. The source of order. Prigogine. Far from equilibrium, studies led me to the conviction that irreversibility has a constructive role. It makes form. It makes human beings. Irreversible time is not an anomaly, but relates to reversible time. This is not an either-or situation. Reversibility applies in closed systems only. Irreversibility applies to the rest of the universe. And chaos is the arrow of time. A chaotic mystery. Why is Prigogine so conspicuously absent from all works on chaos and complexity? Other features of self-organization. Prigogine defines self-organization as the phenomenon by which a system self-organizes its internal structure independent of external causes. Such self-organizing systems also exhibit other properties of chaos: non-linearity, feedback, fractal structures, and sensitive dependence. The French physicist Bénard provided a demonstration of self-organization, even before Prigogine had come up with the notion. Bénard's experiment works as follows. He placed some liquid in a vessel and heated it from below. At the beginning, when the temperature difference between the heated base and the cool top was low, the heat was transferred by conduction and no macromotion was observed in the liquid. Later, however, as the temperature difference between base and top increased, a certain threshold was reached. The movement in the liquid became unstable and chaotic, and then suddenly an ordered pattern appeared. The molecules of the liquid, which had been moved at random, suddenly exhibited a clear macro movement in rolls which were millions of times larger than themselves. When the liquid was contained in a round vessel, the motion of the rolls formed a hexagonal pattern on the surface of the liquid. This pattern is the result of hot liquid rising through the center of the honeycomb cells and the cooler liquid falling along the walls. All this appears to be the result of a force, but no such force is present. The order is spontaneous. It is self-organization in action. Self-organizing systems have three main features. They are open and part of the environment, and yet they can attain a structure and maintain it in far from equilibrium conditions. This undermines the traditional view that systems must be examined as if they were isolated from their environment. These systems also run contrary to the second law of thermodynamics, which states that they should move towards molecular disorder and not order. The flow of energy in these systems allows them spontaneously to self-organize, creating and maintaining a structure in far from equilibrium conditions. Such systems also create novel structures and new modes of behavior. Self-organized systems are thus said to be creative. Self-organized systems are complex in two ways. First, their parts are so numerous that there is no way in which a causal relationship between them can be established. Second, their components are interconnected by a network of feedback loops. Life itself is an expression of self-organization. Period 3, chaos. Tian-Yen Li and James York, two mathematicians working at the University of Maryland, are credited with coining the term chaos. The term was first introduced in their much-quoted paper, published in 1975, with the peculiar title, Period 3 Implies Chaos. What is period 3? A sequence of period 3 is one in which each state is identical with the state that occurred 3 steps earlier, but not with the state that occurred 1 step or 2 steps earlier. Lee and York showed that it was impossible to set up a system that would repeat itself in a period tree oscillation without producing chaos. York explains his discovery in these words. In any one-dimensional system, if a regular cycle of period tree ever appears, then the same system will also display regular cycles of every other length, as well as completely chaotic cycles. Let's put this in another way. Consider a population of, say, insects. For a given population, when the parameter rate of population growth R is increased, the population initially increases too. Then at a critical point, two lines appear, the bifurcation. This corresponds to a population going from a 1 year to a 2 year cycle. These two lines would double again as the parameter was raised and the pattern of population repetition slowly broke down. Suddenly, chaos would appear with whole sections of the graph blacked in. Then, just as suddenly, windows of regularity would appear, always odd, like 3 or 7. This meant that the population was at this moment oscillating around at 3 or 7 cycle. Any system that repeated itself in a period 3 oscillation would produce chaos. It cannot exist without it. This technical description of chaos seems to fit the non-technical definitions of chaos. Thus, whether they intended to or not, Lee and York succeeded in establishing a new scientific term. Chaos is a loaded term. Its widespread application as the name for a new science, a new perspective of the natural world, not conveying the precise clarity of the nature of the phenomena that is the methodology as it is made apparent. Many scientists consider chaos to be a poor name for the new science because it implies randomness. For them, the overriding message of the theory is that simple processes in nature can produce edifices of complexity without real randomness. In nonlinearity and feedback, you have all the necessary tools for encoding and then unfolding structures as rich as the human brain. Yet chaos is the name, and the name has stuck. Towards the edge of chaos, complexity theory. In the 1980s, the study of chaos moved deeper into real-world situations. Scientists began to produce experiments which sought and found chaos in physical systems. This was significant because it took chaos from the realm of theoretical abstraction to being an objective characteristic of nature. At the same time, the phenomenon at the edge of chaos began to attract greater attention from scientists in most disciplines, and the contours of an even newer science began to appear: complexity. What is complexity? The nonlinear dynamic systems studied by chaos theory are complex systems in the sense that a great many independent variables are interacting with each other in a great many ways. These complex systems have the ability to balance order and chaos. This balance point, called the edge of chaos, where the system is in a kind of suspended animation between stability and total dissolution into turbulence, has many special properties. Complexity is the new science of complex systems. It studies life at the edge of chaos and explores the properties of complex systems at that state. What special features do complex systems exhibit at the edge of chaos? The sheer richness and diversity of interactions between a host of interdependent variables allows complex systems to self-organize. The process of self-organization happens spontaneously, as though by magic. Think of a flock of birds taking off to fly to their place of migration. They adjust and adapt to their neighbors and unconsciously organize themselves into a patterned flock. Through the simple acts of buying and selling, people organize themselves into an economy. And it happens automatically, without anyone leading the process or consciously planning it. Atoms form chemical bonds with each other and organize themselves into complex molecules. Spontaneous self-organization is one of the main hallmarks of complex systems. Adapt and relate. The other main characteristic of complex systems is their adaptive nature. Complex systems are not passive. They respond actively to transform whatever happens to their advantage. Species adapt to changes in the environment. Markets respond to changing circumstances, prices, technological advances, changes in style, etc. The human brain constantly organizes and reorganizes its billions of neural connections to learn from experiences. Complex systems also highlight the interrelatedness of things. Complexity emphasizes the interconnection of all things. Everything is connected to everything else. Trees with climates, people with the environment, society with each other. We no longer stand alone, nothing does. What is the difference between complexity and chaos theory? Complexity is concerned with how things happen, whereas chaos tends to observe and study unstable and aperiodic behavior. Chaos seeks to understand the underlying dynamics of a complex system. Complexity grapples with really big questions. What is life? Why is there something rather than nothing? Why do stock market crash? Why did the Soviet Empire collapse within a few months? Because it only accounted for one market. Why do ancient species remain stable in fossil records through millions of years? Science journalist Roger Lewin says that as the theory of life at the edge of chaos, complexity includes the entire spectrum, from embryological development, evolution, the dynamics of ecosystems, complex societies, right up to Gaia. It is a theory of everything. Beyond entropy. Complexity's greatest contribution has been to show that the second law of thermodynamics is not the whole story. The second law introduces the arrow of time into physics and states that the entropy or disorder in the universe can only move in one direction. It can only increase. The universe is doomed to an ultimate state of absolute disorder. Complexity shows that not all systems tend towards disorder or entropy. Nature contains deep order, which is believed to emerge naturally. Emergence. New variables occur over time and do not require an outside force in order to be. This is not a problem for physicists, but is more of a problem for biologists, because it appears to contradict Darwinian ideas. A great deal of recent research on complexity has been carried out at the Santa Fe Institute, an interdisciplinary center of excellence which was established in 1984 with the specific purpose of developing the theory of complexity. Together, chaos and complexity seem to be driving our world. Everything that is real is chaotic. Spaceflight, electronic circuits, deserts, ecology of jungles, the stock market, national economies, the list is endless. And all living systems, the most physical systems, are complex systems. Given their complementary features, it makes sense to combine chaos and complexity together. Chaotics. This is what three European scholars, George Anderlaw, Anthony Dunning, and Simon Forge, suggest. Together, chaos and complexity spell chaotics. Chaotics, they suggest, could be used to create a framework within which novel solutions to problems could be found, as new ways of thinking about and solving problems are explored. Chaotics not only affects the answer, but the thought that provokes the question. Let's see how chaos and complexity, or chaotics, applies to the physical world and how it is changing our perceptions of life, the universe, and things in between. Chaos and cosmos. Complex dynamics are going on everywhere in the universe. Galaxies swirl around, supernovas explode in shock waves, giving birth to stars and cauldrons of chaos. Black holes swallow up passing energy. Neutron stars spin at frantic rates. Planets display fractal patterns, signposting chaotic processes going on at their surfaces. Poincaré's discovery. Before the advent of chaos theory, the solar system was seen as a perfect example of a celestial mechanics. This despite the fact that at the beginning of the 20th century, the French physicist and mathematician Henri Poincaré, 1854 to 1912, had shown that there were serious problems when one considered the orbits of more than two celestial bodies. He plotted the orbits of 3 planets qualitatively in phase space and then examined a section of their trajectories. My solutions suggest that the presence of a third body could cause a planet to gyrate, wave, or even fly off. What Poincaré had discovered, although he and others did not know it at the time, was chaos. Poincaré's discovery, implying that the solar system was chaotic, a few decimal points away from annihilation, was neglected for decades. The conditions of stability. In the 1950s and 60s, 3 Russian scientists, Andrei Kolmogorov, Vladimir Arnold, and Jürgen Moser, picked up Poincaré's work. They discovered that stability in a 3-body planetary system requires 2 essential conditions. The first involves resonance. Any 2 periodic motions can be in resonance, such as 2 moons moving around a planet. If one circles the planet once while the other goes around it twice, they are in a 2-to-1 resonance. Also, they may be both in resonance with the planet's own orbit. It's a bit complex to visualize. The graph slightly helps. I'll go get some water and I'll be back. And we're back. Hydrated, which is a bit easier when you're narrating or reading a book. Okay, so now we are at the idea of quasi-periodic stability. For 3 planets to be in stable orbits, it is necessary that their resonances are not in simple ratios like 1-to-2 or 2-to-3. In order to remain stable, the planets must be quasi-periodic. That is, the periods never exactly repeat themselves. If the periods do repeat themselves, the perturbation may be amplified with each orbit and resonance sets in. This is the same as positive feedback. Small events in this situation can have a major effect. The planet's orbit could snap, sending them whizzing off through space. The KAM theorem, or the KAM theorem, the second condition of stability, involves gravitation. This condition the Russian scientists formulated as a theorem. The KAM theorem named after the initials of their surnames, states, if you start with a simple linear system for which a solution exists and add a small perturbation, the system will remain qualitatively the same. Interesting. In other words, if the influence of the third planet is no bigger than the size of the gravitation attraction of a fly in Australia, the three bodies will remain in stable orbit. Unfortunately, our solar system does not rigorously satisfy these conditions. Saturn's moons. Studies based on the results from Voyager 2, which flew past Saturn in 1981, have shown that many of the moons in the solar system have been in a chaotic state at some time or another, before stabilizing into quasi-periodic orbits. Hyperion, an oblong-shaped moon that tumbles around Saturn, is in such a state at the moment. Other moons, such as Neptune's largest moon, Triton, have cannibalized celestial satellites while in a chaotic state. Astronomers believe that the orbit of Pluto may also occupy a chaotic region. Chaos prevents asteroids from locating at certain parts of the solar system. This is why there are gaps in the asteroid belt between Mars and Jupiter. Gaps in orbits also exist in the rings of Saturn. These gaps appear to be the result of feedback effects of gravity exerted by Saturn and its moons, which make the regions chaotic and therefore unoccupiable. A chaotic universe. Astronomers are a long way from formulating a model of the creation of the solar system based on chaos, but we no longer see the solar system as a simple mechanical clock. This is a constantly changing, complex system. Do you think there's a butterfly flapping its wings out there? Quantum chaos. The universe could itself be a product of chaos. It is commonly supposed that some fluctuations created the galaxies, fluctuations that happened near the beginning of the formation of the universe. Chaos may have played a part in this. The universe was in a state of near chaos at the time, and the only valid description of what happened is a quantum description. Therefore, what happened may have been quantum chaos. To understand this idea, we should look briefly at the theory of quantum physics. Brief history of quantum theory. Quantum physics is a theory of the microcosm which applies only to the atomic world. Since the 1920s, we have known that the classical physics of Newton is only an approximation of the physics that describes the subatomic world. In the mid-1800s, scientists began to realize that certain events did not correspond to Newton's laws. The main problem with the radiation is that a metal, when heated, gives off more radiation at certain frequencies than others. The path of ball might, but not the radiation curve of an heated object. So, differences in reactivity. For an imaginary body known as a black body, the graph of radiation intensity versus frequency has a very well-known curve. The black body problem. The amount of radiation emitted peaked and then fell off. The peak would be in different places for different temperatures. No one knew what was going on until Max Planck, 1858 to 1947, a German professor at the University of Berlin, realized that classical physics was not working. I decided to envisage the radiation coming off the object, not in a constant stream, but in chunks, or quanta. I assumed the existence of a new constant calling it h, in order to make my curve fit the experimental one. At first, this assumption bothered him, but it worked well and led to the startling new discovery. Planck's constant, as it is known, was related to the structure of atoms. And so we'll end the lecture there today, and we'll be starting on the application of the Planck's constant by Rutherford and Bohr. and then we'll move on to de Broglie, Schrödinger, and Born. All of these thinkers having created the foundation of quantum mechanics and quantum physics, which will then provide a better picture of the modernity in which we live and the ways in which chaos theory might apply to this modern and precisely maybe postmodern, but postmodern brings us back to modernity as far as we chose to characterize it in a certain way. And so, let us leave the dialogue open for now.